So last week, we started to, calculate the predictions from Hartree-Fock theory. And as I mentioned last time, the Hartree-Fock theory fails in all aspects, comparing to the experiments for ordinary metals. But still, the Hartree-Fock theory is a very useful lesson that we can learn a great deal of physics from. So let's just continue this, calculating these Hartree-Fock predictions. So the first quantity that we would like to compute is the quasi-particle excitation energy, or the particle-hole pair energy for ordinary metals near the Fermi surface. So last time, we started to compute this energy cost required to put the one electron in the excited state with the momentum p prime, which is given by this partial derivative of the Hartree-Fock energy, with respect to the occupation number, which is the energy required to put the electron in the state p prime per electron number, and which is given by this result. And remember, this first term comes from this Sommerfeld free electron kinetic energy. And the second term comes from the exchange energy of a Hartree-Fock approach. But this is just half of this energy required to have such an electron-hole pair, because there is a hole leaving behind this field electron state inside the Fermi sphere. So we need to take this energy into account. But we know that to create a hole at a state P, the energy cost for that process is actually negative to the energy required to put the actual electron in a state P prime, because the energy associated with the hole is actually negative to the actual energy cost to put the electron in the empty state. So we need to take energy out to create a hole, and therefore the energy cost to create such a hole is actually negative, which is negative. All right? So the total energy required to create such an electron-hole pair is the sum of the two energies. So one is positive, which means that we need to put the extra energy, which is positive, but the other whole energy is actually negative, meaning we take energy out of the system. We need to really subtract the magnitude of these two energies from each other to get a total energy requirement to have such an electron-hole pair. And therefore, the total energy is the difference between these two derivatives, because of this statement here. So let's just compute this total delta W, which is the total energy requirement to have such an electron-hole pair. And as I mentioned, this electron-hole pair are generated near the Fermi surface. So these two energies, P and P prime, are very close to each other, or the momentum difference is not that large. So we assume that this two momentums, P and P prime, are very close to Fermi momentum, Kf. So we could do Taylor expansion very close to Fermi surface of these two momentum, P and P prime. And when we do that, you simply just Taylor expand these two derivatives, and you get to this form, where delta P refers to the momentum difference between P and P prime, and we also need to multiply this sort of a second derivative of Hartree-Fock energy, but one with the occupation, another respect to this momentum. Okay, so if you simply just move this delta P to the left of this equation and take the limit where delta P goes 0, so that this is the derivative of this energy respect to momentum, which is given by this result. And the first term comes from, again, this free electron thermophile gas carrying this kinetic energy epsilon p, and the second term is from this Hartree-Fock exchange energy. So then this total energy associated with such elementary excitation is given by this derivative evaluated close to Fermi energy multiplied by this momentum difference, delta p. All right? So the problem with the Hartree-Fock prediction is that this derivative, the WdP, diverges. For a free electron thermophile gas, we know that the energy required to have such an electron-hole pair is really tiny, because if the electrons are free and they don't interact with each other, so as we just argued and calculated earlier, that the energy cost to have such a process is really, really small, and especially when the electrons are precisely at the Fermi surface, and you know that the quasi-particle lifetime is infinity. So they live forever. Remember that, right? So the quasi-particle electron-hole pair live almost forever when they are very close to Fermi energy, which means that it's really easy to have such a particle-hole excitation. So this quantity for the free electron thermophile gas is actually a constant, okay, near the Fermi energy, and this constant multiplied by a small, momentum difference. When this delta P goes 0, this total energy vanishes. So this is the correct picture, that even in the presence of a Coulomb interaction, and to create such an elementary excitation is really not that hard, which means that delta W should be very small, even approach 0. So that's what we expect. But what comes out of the Hartree-Fock theory is that this delta P diverges. It approaches infinity. The way that they diverge comes from the fact that this derivative, the WdP, evaluated at epsilon f, really goes like 1 over delta P to the power of 3. It's a cubic in delta P in the denominator. And then, of course, you have a delta P in the numerator. But when you cancel this, you still get 1 over delta P squared, and you sum over all this momentum very close to Fermi momentum. And when delta P vanishes, this actually diverges to infinity with a speed that is proportional to 1 over delta P squared. So see that the Hartree-Fock theory cannot reproduce what we expect at low temperatures for ordinary metals. That is very easy to create elementary excitations. But within Hartree-Fock, it's almost impossible to create such an elementary excitation. Of course, it is wrong. Of course, this is not correct. But we need to understand why this Hartree-Fock theory fails, and the reason that it fails is because the Coulomb interaction is actually long range. Okay, as I mentioned many times, that within Hartree-Fock, the Coulomb potential is always 1 over r, and with this long tails all the way when r goes to infinity, which means that the two electrons can feel the Coulomb energy or Coulomb interaction, even they are really far away from each other. But we know that they should not feel anything if they are sufficiently far away from each other. Okay, so and that will lead to this realistic picture in the realistic solid, that this Coulomb potential or Coulomb force is actually screened. There's a screening effect of a Coulomb potential which cut off this long-range tails in the realistic solids. So in the realistic materials, the Coulomb interaction goes like this, So when the distance between these two electrons is over some critical distance, then these two electrons feel almost nothing because the Coulomb potential decay exponentially. So for the distance goes over this critical value, say 1 over alpha, then this Coulomb potential decays as, say, e to the minus 1. Okay, so you could very clearly see that in realistic metals, Coulomb potential is really screened. It's not long range. But this screening of a Coulomb potential is not captured here within the Hartree-Fock, which makes this theory, wrong or fail. But here comes the question: so how can we capture the screening of a Coulomb potential so that this is short-ranged, not long-ranged? So we need to totally abandon the starting point of a Hartree-Fock theory, meaning, we should not do this perturbation theory based on the SOMO ferroelectron gas and then put the Coulomb interaction as a small perturbation. So this kind of approach will naturally lead to such trouble. So we need to give up this kind of a simple and naive approach to this, say, a Coulomb effect in metals. So we need to find alternative way to really capture the screening effect. But what is the correct approach then? Right? So this is our next job, is to really focus on sort of a screening of a Coulomb interaction. So the screening refers to the fact that in addition to these isolated electrons, electron 1 and 2, in the realistic materials, there are many charged particles. Some of them are positive ions, and others are negative charged electrons. So there are many electrons and ions in between these two electrons. So that effectively this Coulomb potential fueled by this electron 1 and 2 will be strongly affected by this kind of a charged clouds in the middle. So this kind of charged cloud will lead to this reduction of Coulomb between electron 1 and electron 2. And this is precisely the screening effect. Okay? So, and this is the correct way of thinking about this Coulomb interaction in solids, because there are so many charged particles. And when you calculate this Coulomb interaction between any two charged particles, you need to also include the effects of all other charged particles. So everybody influences everybody else. So that's the reality. All right? So it's some kind of a butterfly effect. So you know what the butterfly effect? There's a movie called the butterfly effect, right? So a ripple somewhere in the universe, or on Earth, say in Taiwan, is going to affect far away, say some kind of fluctuations of some waves, say in Africa or somewhere else. So which means that all these electrons are not independent particles anymore, because they mutually influence themselves. So we cannot isolate these two electrons and study the Coulomb potential between them anymore in the realistic materials. We need to take into account this kind of a charge fluctuations for all the charged particles in that system. And this tells us that sort of a unit or the basic principles that will lead to the screening effect should be the density fluctuations. So we need to take these density fluctuations or charge density fluctuations into account more seriously, and we should reformulate our Hamiltonian for metals in terms of the density operator, electron density operator. So we will go back to this just a moment, but we should again describe another wrong predictions made by Hartree-Fock theory. So let's take a short break. When we come back, we will calculate another quantity which again tells us that Hartree-Fock theory fails in every way. Well, in semiconductor, you may not have such a simple, naive looking picture of this Fermi surface and elementary excitations because there is a gap, right? There's a charge gap between the valence and conduction band in semiconductors. So, of course, this will influence the energy requirement to have such an electron hole pair excitation. So we are talking about metals, ordinary metals without the charging gap, so that the homotherapy electron model applies. But for semiconductor, you need to think about the energy gap, right, when you calculate this electron hole pair excitations. So that the gap will really constrain the probability to create such a electron hole pair excitations exponentially, right? But then the Hartree-Fock fails to describe everything. I'm saying that in solid state materials, Hartree-Fock theory fails to describe metals, fails to describe insulators, fails to describe ferromagnets, fails everything. I'm not saying that it's totally useless. I'm saying that the theory fails in every aspect in solid state material. And yet, this is very important first lessons. Maybe the Hartree-Fock theory is successful in other systems, like quantum chemistry. I know that there are some approaches, right, in quantum chemistry is based on the Hartree-Fock. I'm not expert in quantum chemistry, but in solid state that we are talking about in this course, okay, it's totally, I'm not saying it's useless, but it's very useful for pedagogical reasons, but not for practical applications. So it's very valuable theory, but it's interesting, it fails. But what can we do, right? So we can only learn from our failures. So this is a really important lesson. As you know that because of this divergence in this electron hole pair excitation energy, this similar divergence appears in all quantities that you can think of. For example, the quasi-particle energy. So the second is quasi-particle energy. Remember that this epsilon k for free electrons, homothermal gas, is just the kinetic energy per electron. But within the Hartree-Fock, we have the exchange energy that we should include. So the Hartree-Fock energy included in the electron energy per particle, and this is given by this quantity. So this is simply just given by the partial derivative of Hartree-Fock energy respect to this Nk. So this is similar to the Wp or Wp prime to really create a single electron or take one electron out to create a hole. So this is simply just Wk, which is the single quasi-particle energy. So this is the kinetic energy, and this is potential energy. So as you can guess, because this momentum K prime is very close, and also K are very close to the Fermi energy at low temperatures, and which would contribute to this, contributions to this summation over K prime, because there's a Fermi function here. When that happens, this divergence is really easy to see because this is kind of a delta K or delta P, and then when this delta K or delta P goes to 0, this diverges logarithmically. So we could really see that divergence. So let me just isolate this exchange energy, which is minus and volume integral dk prime 1 over k minus k prime square. All right, so this is nothing but this integral, at 0 temperature. And this is actually logarithmic divergent quantity right here. So this is going to be something like E squared kf over m 2 plus kf squared minus square divided by k kf log k plus kf k minus kf. So when you integrate out this momentum k prime over this 1 over k minus k prime square, you get the log function. And immediately that when the denominator vanishes, which means that when k is very close to kf, you get the log divergence. So this diverges logarithmically, and which again invalidates our expectations that you should not get divergent immensity, say quasi-particle energy, because we know that this energy should be very close to the free electron kinetic energy with some modifications within the this Landau's Fermi liquid theory. So suppose we calculate this density of states at Fermi level for such a Hartree-Fock electrons, and we get this density of states is actually inversely proportional to the slope of your dispersion. And because of this logarithmic divergence in its energy, and if you take the derivatives, this Hartree-Fock energy with respect to momentum evaluated at kf, and you get the log divergence, right? So 1 over log, which is 0. All right, so which means that there is no density of states at the Fermi level within Hartree-Fock. No density of states in Hartree-Fock. Okay, so how could that be? Of course, it is not reasonable because we know that the electron density of states for ordinary metals near the Fermi surface is finite. It does not diverge. But the Hartree-Fock theory predicts the divergence, and you know where this divergence comes from. So this divergence precisely comes from this long-range tail of the Coulomb potential. So once this long-range tail is included here, and the divergence will follow all the way to all the thermodynamic quantities. Okay, so the divergence is unavoidable. So it is here and there, it is everywhere. So we can understand why this Hartree-Fock theory fails because of the long-range Coulomb tail. So let's just look at the specific heat. Again, the CV, which is the specific heat of this Hartree-Fock metal, goes like T over log T. Of course, this is wrong because we know that for ordinary metals, CV is actually linearly proportional temperature for electronic contribution to the specific heat. So that's CV over T, which we call this gamma coefficient, as a constant for ordinary metals. But within the Hartree-Fock, it goes like T over log T. So you see that log T or logarithmic divergence is present in all quantities. So that's, it fails in all aspects because of this logarithmic divergence. And even though this is a wrong prediction, but this is an interesting homework exercise. So derive it. Again, go back to the Hartree-Fock energy and calculate the internal energy of the system, and following the statistical mechanics textbook, and you can calculate the entropy and take the derivative to the entropy with respect to the temperature. You get some sort of a specific heat coefficient. So I guess that should be enough examples to demonstrate that this Hartree-Fock theory fails in all aspects. But still, it is a very good lesson to be learned at this early stage when we try to study the Coulomb interaction in ordinary metals. So the final example to show this failure of the Hartree-Fock theory is to show that this theory ignores the opposite spin correlations, the correlation between spin up and spin down electrons, different spins. As was discussed earlier, some of you asked this question in class, right? So in the Hartree-Fock theory, spin up electrons always interact by Coulomb with another spin up electrons, because there is no way in the Hartree-Fock theory that the spin up electrons will interact with spin down electron. Okay, which means that the Hartree-Fock theory favors the ferromagnetic couplings. And we will see that in just a moment, favors ferromagnetism, which means that it favors the situation where all the electrons are pointing to the same direction in metals. So which leads to this prediction, of course this is a wrong prediction, of a ferromagnetic metals in Hartree-Fock. So you are about to see that this kind of prediction is reasonable. Of course this is wrong, but it is reasonable within the Hartree-Fock language. So suppose we consider two situations. The first is that the metals are non-magnetic, meaning all the states or energy levels for those electrons are already doubly occupied. So if the electron numbers are even numbers, then all the electrons are really paired up, so they fully occupy to any electron energy levels, so that there's no net spins or magnetic moment, and which corresponds to regular Fermi sphere or regular Fermi surface. But in contrast to these non-magnetic metals, the Hartree-Fock theory favors the ferromagnetic metals in a way that all electrons can only occupy singly in these energy levels, so there is no double occupancy, so that all the electrons are singly occupied, so that it has the maximum number of fully polarized spin moment. So there is a net spin moment which maximizes this kind of magnetic moment if they fully are along to a certain direction, say spin up. But in such a case, you need twice as many states as this non-magnetic case, because now the energy levels, say this is N non-magnetic and this is N ferro. The N ferro is actually 2 times N non-magnetic, because the total electrons are the same, but they just don't want to have neighbors. They just want to take a seat by themselves. For the same total amount of electron numbers, but in the ferromagnetic case, it needs twice as many energy levels to populate the same electron numbers. Is that clear? Right? So, but the consequence of this doubled energy levels, the number of energy levels implies a bigger Fermi surface. So the size of this Fermi spheres for the ferromagnetics is actually twice as large as this non-magnetic case. So suppose this is volume ferro, which is 2 times volume of non-magnetic, and therefore this modifies both the kinetic energy and the potential energy within the Hartree-Fock, and also compared to the non-magnetic case. So you could actually compute this energy difference, which is total energy of a ferromagnetic states minus the total energy for non-magnetic metals. And you will find that it is very easy to have the situation where this delta energy difference is actually negative, satisfied. All right, so I used up all this space. So I would just finish up the last part of the calculation after the short break. So let me just summarize this result. So within the Hartree-Fock, suppose we calculate ferromagnetic metals, and the total energy is actually lower than the non-magnetic metals within the Hartree-Fock. And therefore, if these two states are competing with each other, then the low energy state wins, right? So from this principle of thermodynamics or statistical mechanics tells us that if there are many, many states are possible ground states, but only the states that have the lower energy is actually more stable. So, which means that within the Hartree-Fock, the ferromagnetic states is actually lower in energy, and therefore it is more stable compared to the non-magnetic case. So that this is favored by Hartree-Fock. But you know that there are not so many ferromagnetic metals in real life. But the Hartree-Fock theory incorrectly predicts that there are so many ferromagnetic metals that are predicted or favored by Hartree-Fock, which of course is not correct. So this is another failure of the Hartree-Fock, which incorrectly predicts these ferromagnetic metals. But in reality, there are not so many cases of ferromagnetic metals, but most likely they are non-magnetic. If they don't have the spin-spin interactions in the systems, and most likely they are non-magnetic, but the Hartree-Fock incorrectly predicts that they are ferromagnetic. So after the short break, we will finish this calculation, and again, there will be another homework to actually convince yourself that indeed the Hartree-Fock theory fails, but we need to know why it fails. Okay, so let's take a short break. Any questions?
As you talked, if we include the spin-spin interaction, then it can recover this fail.
Well, this is a good question. So suppose we include the spin-spin interaction, right? So you know that it's not possible within Hartree-Fock, because you know that all these Coulomb interactions are between spin species, right? So even though we want to include this up and down spin correlations, but there's no way. So even if we want to, that's how? There's really no way to include spin-spin interactions within the Coulomb form. Of course, if you include kind of a spin-spin Heisenberg-like couplings, that's another story. But here we are talking about the Coulomb. There's only Coulomb here, nothing else. But within the Hartree-Fock, the Coulomb is just the interaction between same spin species, and there's no way that we could fix this problem. Okay. Sorry and sad, but that's the reality. So let me just finish this calculation to show that the Hartree-Fock theory favors the ferromagnetic metals. As I mentioned previously, that compared to the non-magnetic case, in the ferromagnetic metal, the Fermi volume is that twice as big as that for a non-magnetic, because all the levels are singly occupied to get maximized spin polarized case for the ferromagnetic situation. And so the energy difference between these two cases is given by these two quantities that you subtract from one another. And in particular, for a ferromagnetic case, because the Fermi volume gets 2 times bigger, so that leads to the increase of this Fermi momentum, Kf by 2 to the power of 1/3, right? Because this, if you cubic this value, this is 2, right? So the radius of this Fermi sphere should be that much compared to K0. So then, and this will affect all this kinetic energy and potential energy, when you calculate this energy difference. So that you can simply just separate this kinetic energy from this potential energy in these two cases, and you subtract this kinetic energy for the ferro from this kinetic energy for the non-magnetic, and also for the exchange energy, you simply just subtract from one another. But remember that when you calculate this ferromagnetic case, the Fermi momentum changes its magnitude by this 2 to the power of 1/3. That's much. So you simply just plug in the kinetic energy for the Hartree-Fock exchange energy of the Hartree-Fock by replacing this Fermi momentum by the new value, and you subtract this by the non-magnetic values, and you'll find that this is your final result. So the first term is what's this 1.3 divided by Rs squared, and the second term is negative 0.238 divided by Rs. So you can see that if Rs is actually larger than this critical radius Rc, which is about 5.5, then this delta, the energy difference, is negative, which means that the ferromagnetic state is more stable. But if Rs is actually smaller than Rc, then this delta is positive, so that this non-magnetic state is more stable. So, which means that the Hartree-Fock theory predicts when Rs is greater than the critical value, those metals should be ferromagnetic. But of course, these predictions are wrong, because if Rs is bigger than Rc, still many metals are non-magnetic, and they are not ferromagnetic metals. But this is a very good exercise for you to actually derive this estimation simply by comparing the two situations, the ferromagnetic and non-magnetic, and plugging this correct Fermi momentum in the ferro case, and then you will get this estimation. So it's a simple homework exercise. So now we should totally abandon this Hartree-Fock approach, and as I mentioned, to describe this screening of a Coulomb potential, we need to find more fundamental, degree of freedom to reformulate our Hamiltonian, and to really proceed this reformulation of a Hamiltonian for a Coulomb interacting electron gas. We should briefly describe or mention the semi-classical approach to the screening of a Coulomb potential. So, of course, this phenomena at the classical level is known, that if there are some charged particles in between isolated two charges, and this will affect or reduce the Coulomb potential between these two isolated charges. And we know that already, but here we are talking about the quantum mechanical system. At low temperatures for ordinary metals, we still can see this screening of Coulomb interaction, but a simpler approach is so-called the Thomas Fermi approximation, which kind of combine the classical electrodynamics and quantum mechanics. Okay, so it's not a rigorous approach, but sort of it could actually capture at a qualitative level how this screening occurs. So, as I mentioned, we need to consider a kind of a charge fluctuations. So this is some kind of a charge distributions in real space, and we know that there's a lattice spacing A, and there's some charge, static charge Q, and there's a isolated static charge Q right here, very close to some kind of inhomogeneous charge distributions over entire space. But that static charge Q will actually affect the charge distributions right there, because there's a feedback effect, right? So there's a static charge, and this charge will certainly disturb this charge distributions nearby, and therefore it creates some kind of a charge disturbance, delta rho, right here. And we would like to really calculate this kind of a feedback effect on both static charge Q and also this kind of a charge disturbance. So this is the so-called Thomas Fermi approximation, and this is a way to calculate the electron response to a static charge Q in a plasma, which is kind of an electron soup. So the spatially inhomogeneous charge distributions, kind of a disturbance, varies very little over an atomic scale spacing, A. And the Fermi energy is also slowly varying in space, which means that this momentum transfer is actually much smaller than the Fermi momentum, or the long wavelength limit. So we could actually combine quantum mechanics and electrodynamics. So this is the kinetic energy of an electron in quantum mechanics, and this is the Fermi energy, and this is the electrostatic potential. So we can consider that this electron near this static charge here is almost free. It's almost free, and so it actually is influenced by this kind of electric static potential, and then this is the relation in quantum mechanics. But we also have this classical Poisson equation, which tells us that this second derivative or Laplacian of this electrostatic potential is actually the sum of these two contributions. One is the static charge, another is the response of that static charge, delta rho. So this and this kind of a response to Q. So the response charge is actually negative to the static charge because of the kind of classical electrodynamics, that the induced charge is really carrying the negative sign relative to the so-called test charge. So if you have a test charge here and next to some metals with many charge or electrons, and this test charge is going to induce negative signed charge on the other side, right? So if the test charge is actually electrons, then on the other side of your charged particles, there will be induced positive charge, okay, and vice versa. So this delta rho carries this negative sign compared to your static test charge. But this psi describes the net potential in your plasma or electron plasma. So which means that this sort of psi describes the net potential, electric potential, by combining both the effect of a static test charge and also this disturbance or induced charge effect. All right, so that's from classical electrodynamics, that you have the Poisson equation, which describes the net potential that combines these two effects. So the Thomas Fermi approximation is the approximation that you simply just combine these two. Of course, this is not an exact approach, but you could actually capture qualitative features of this screening of a Coulomb potential by simply just combining this quantum mechanical equation for the electron kinetic energy and potential energy, and also the classical Poisson equation. So let me just define more precisely this delta rho. Delta rho is the change in electron density near the test charge Q due to this charge. So now we could simply just combine this kind of a relation from quantum mechanics, from Schrödinger equation, and the classical EMM, which is the Poisson equations describing the net electric potential in this electron plasma. So by combining these two relations, we are able to describe the screening of a Coulomb potential, which means that this psi of R is no longer simply described by this, this long range 1/r tail, but it is really cut off by this exponential decay factor. So if you solve those two equations together, you will find that the psi of R is no longer simply just long-tailed 1/r Coulomb potential, as we know very well. Let's take a short break. When we come back, we will solve these two equations simultaneously, and we will again use these two approximations that this inhomogeneous charge disturbance is really, really slowly varying in space over atomic spacing A, and also the Fermi energy. So now you know this Fermi energy is, in this formulation, is a function of distance, or it's a function of r, because you get a potential, external potential here. So the Fermi energy is no longer just constant, but it also varies in space. But the assumptions behind the Thomas Fermi approximation is that this Fermi energy is also very slowly varying in space, so that we could make some approximations and we can proceed these calculations. So let's try to solve this combined equations from quantum mechanics and the Poisson equations. So we know that this charge distributions of this plasma or electron soup can be considered as just a background uniform charge density plus some variations. And this variations is nothing but just this charge disturbance that is induced by this test charge Q. So this is a disturbance induced by charge Q. So we could simply just calculate this kind of net charge distributions, rho of r, quantum mechanically, because we know that this is related to this Fermi momentum. So from your free electron somatoform gas, you know that this electron density is related to the Fermi momentum, the cube of Fermi momentum, and divided by 3 pi squared. So that's already known. But what is K0? So you could simply just use the first equation to rewrite your K0 in terms of this Fermi energy and the Coulomb potential. So I simply just rewrite this K0 by plugging this first equation from, say, quantum mechanics. But here comes the approximation. So this is given by n plus delta rho. So here n refers to the constant charge density given by the free electron gas, and delta rho comes from the disturbance induced by the test charge Q. So under the assumption that this E psi is actually a small disturbance compared to the Fermi energy, this kind of a net electric potential is really, really small compared to the Fermi energy because of this kind of a small charge disturbance induced by the test charge Q. This is Q and delta rho. So we could simply Taylor expand this epsilon f plus E psi to some power. So we could linearize this rho of r under such a assumption, so that delta rho is approximately given by this linearized form. Okay, so you can simply just Taylor expand this by assuming that this epsilon f is large enough. So this epsilon f times 1 plus E psi over epsilon f, and this power of 3/2, and you could simply just do Taylor expansion. So there's 1 plus that small something, and which leads to this prefactor 3/2, and comes from this Taylor expansion of this factor. All right? So now you could simply just rewrite your Poisson equation in terms of this linearized form of delta rho. So you know what this delta rho is. So you plug in this to this Poisson equation, and this leads to this simplified Poisson equation. So now you could solve this simplified or modified Poisson equation because you know everything, right? So this is known, this Q is known, and this n is known, constant. Epsilon f is known, and so you could very easily solve for psi of r. How do you solve this? Well, you Fourier transform this. We assume that we could Fourier transform this electric static potential psi of r in k space, where k refers to the momentum or wave number, and you plug in this Fourier transform potential. And you get this pi n e squared divided by epsilon f or pi q e to the I k r, which is q over r e to the minus k Thomas Fermi times r, where k Thomas Fermi is given by this constant. It's called Thomas Fermi screening wave vector. So you simply just plug in this Fourier transform back to the Poisson equation, and I'm skipping some details, but you know what to do. So it's very close to your exercise in classical electrodynamics or EMN, and you solve this electrostatic potential by solving this Poisson equation. And the only thing that makes some difference is that there's a constant here. And this constant will lead to the constant in the denominator in addition to the k squared. So once you know that this Fourier transform, this potential, psi of k goes like k squared plus some constant called Thomas Fermi wave vector, then it is straightforward to show that this simply gives you a cutoff. This is your cutoff. And there is a very popular parameters which is inverse of this Thomas Fermi wave vector. It's called Thomas Fermi wavelength, lambda Tf, and this is the solution. So if you plot this electrostatic potential psi of r as function of r, you will see that this is a 1 over r potential, but then it's simply just cut off by exponential factor right at r Thomas Fermi wavelength. So when this r is actually exceeding this lambda Thomas Fermi, then the Coulomb potential get exponential decay cutoff. Okay, so this is 1 over r e to the minus k Thomas Fermi times r. So here comes the correct decay factor, which describes more realistically what happens in metals. But of course, this is just a semi-classical approximation, which relies on assumptions that both the Thomas, this epsilon f and also this charge disturbance vary very slowly over space. Now, of course, we know that in metals, these assumptions are violated in many cases. But again, this is a very straightforward calculation that you simply just combine the quantum mechanics and classical Poisson equations, and this potential cannot be a long range anymore, because again there's a feedback effect. So the feedback effect is precisely hidden in the Poisson equation, that the net electrostatic potential is a combination, is a sum of these two different charge distributions. One is the test charge, another is the induced charge. So you need to take into account the induced charge disturbance. So when you really calculate this Coulomb potential, so this Coulomb potential is no longer just contributed from this test charge or isolated charge anymore. So you need to consider the response from the other charges. And this is the essence of this screening effect, because this induced charge plays a role to cancel this original potential, because the signs of these two charge particles are opposite. So you get cancellations, and precisely the cancellations come from this opposite signs of these two different charge distributions. All right, so this is a more realistic description of what happens in metals, that the Coulomb potential is no longer a long-range force, but it has to be cut off by this exponential decay factor. All right, so maybe we could simply just use 1/3 of the blackboard and to really tell you some requirements or some remarks. So you could find this kind of equations and derivations in many textbooks, including our major textbook, Kittel's second book, Quantum Theory of Solids, and also in David Pine's book, Elementary Excitations in Solids. So let me just make some remarks on the Thomas Fermi approximation. Of course, this is not as rigorous as you could do, but this is a very reasonable thing to do before you solve the problem purely quantum mechanically. There are some requirements. First thing is that the electrons move very slowly so that electrons give rise to only the static disturbance. This is a very important remark because we consider very slowly moving electrons in solids so that the test charge Q will induce only a static charge distributions, which means that this kind of a distribution does not depend on time. But in reality, we know that this is not the case. And we will see in the next chapter that this charge disturbance fluctuates both in space and in time. In reality, delta rho does not only depend on space, but also depends on time, which means that quantum mechanically, we can imagine that because of uncertainty principle, this kind of a charge distributions or disturbance fluctuate back and forth in time. It's called plasma oscillations. And this is purely quantum mechanical effect, which cannot be captured within Thomas Fermi approximation. Thomas Fermi approximation describes only, it's kind of a time-dependent static charge disturbance, which leads to some kind of a cutoff. Okay, but in reality, this kind of test charge is also moving in time, and therefore the induced charge disturbance also moves very quickly in time. And there's a oscillation frequency called plasma oscillation frequency in metals, which can be derived only within the quantum mechanics. But here, this Thomas Fermi approximation cannot capture this physics. So the second remark is that this linearized procedure is valid only when this relation holds, which means that its Fermi energy is much larger than the electrostatic potential, as I mentioned. But this relation is very difficult to satisfy in usual metals, because if you rewrite this in terms of the standard units are S and the Bohr radius are A0, this means that Rs should be much smaller than 1. What is Rs? Rs is the average electron radius in units of Bohr radius, right? Remember that. But in ordinary metals, Rs is somewhere between 2 and 5, which is not small, okay, at all. So that this invalidates Thomas Fermi assumption that Rs should be very, very small. Nevertheless, this Thomas Fermi approximation is still a good approximation to really qualitatively capture this decay part of this Coulomb potential, and that kind of approximation rely on this assumption, but this assumption is not satisfied for ordinary metals. And therefore, to really capture this kind of screening of a Coulomb potential in quantum mechanical system, we need to actually address this issue purely quantum mechanically. So these are the two major remarks, but we will discuss this kind of plasma oscillation phenomena next time. Okay, so I guess that should be enough for today. And please read these corresponding chapters in our textbooks, both the Quantum Theory of Solids by Kittel and also maybe Flansburg. They discuss a little bit about this, and also David Pine's book. Okay, so I'll see you on Wednesday.